Hello everyone, my name is Xiaoyu Hong. Today I'm gonna talk about our recent work named Time Adaptive Change Analysis through the extension of M3C2 algorithm.
To understand Earth's surface dynamics, we increasingly rely on the 4D point clouds. So ideally, we expect a continuous and perfectly uniform 3D observations. However, the reality of long-term topographic monitoring is quite different. So, as you can see on the figures here, we constantly face a major challenge which is the spatial-temporal irregularities. So, especially due to different sensors or varying scanning geometries or even occlusions, our point density is highly inconsistent. So some areas are dense while others are rather sparse. So temporally, our acquisition intervals are rarely perfectly regular. So we might have daily scans during a campaign, followed by a gap of several months. So this inherent irregularities creates a massive gap between the data we have and the requirements of standard analysis methods. So to quantifying topographic changes from 3D data, the M3C2 algorithm has become the gold standard. So how does it work? As shown on the figure on the left, it relies on estimating a local surface geometry. So first, we define a set of core points illustrated as the red cross. And then we define a spatial neighborhood using a spatial radius r. So within this spatial neighborhood, it fits a plane and calculates a normal vectors. On the next step, it projects the points within these spatial neighborhoods onto the axis of the normal vectors. Then we get the mean distance of each epoch. The M3C2 distance is the distance from these two mean positions. However, it relies heavily on having a sufficient local point density. So when in locally sparse areas, there simply aren't enough points to accurately estimate a normal vector. When this happens, the algorithm fails and outputs no results. So instead of a complete map of surface dynamics, we are left with massive data gaps and blind spots. When we look at real-world data acquisitions, as you can see from the timelines at the bottom, we often conducted multiple scans within a single intensive monitoring campaign. Since our temporal sampling frequency is often higher than our required analysis timescale, so why not use this temporal redundancy to mitigate our spatial sparsity? Previous studies like comma and applied a moving window across spatial and temporal domain to filter distance values, and Turbines aggregated multiple consecutive point clouds to create a much denser representations. However, these solutions typically rely on a fixed window approach, where the size of the temporal neighborhood is globally defined. So if we blindly apply global defined temporal windows to aggregate data, we run the risk of oversmoothing. So to solve this missing data problem without smoothing out everything, we developed a time-adaptive aggregation methods. As you can see from the workflow here, we still start by choosing a reference and a target epoch. But before calculating the changes, we establish a spatial neighborhood for every single core point. As shown in the figure here, if a local point density is sufficient, we do nothing. However, if the area is spatially sparse and it falls below our required point threshold, our adaptive aggregation is triggered. So the algorithm automatically opens a temporal search window. It symmetrically expands forward and backward in time, borrowing data from adjacent epochs. We do this symmetrically to avoid introducing any temporal bias into the actual surface changes. It keeps searching until it grabs enough points to accurately estimate the surface normal. But this search does not go on forever. To prevent merging data from vastly different timestamps, the search is constrained by a maximum temporal aggregation window. This window is adaptive and depends on the analysis scale. So, as illustrated on this timeline, if you are comparing a short-term change, say between T0 and Tm, the maximum allowed window search span, shown as the green box, is relatively narrow. But if you are analyzing a long-term change between T0 and Tn, the maximum allowed window scales proportionally. Also, well-covered areas remained completely untouched, so we do not apply global smoothing. We only aggregate in the exact local neighborhoods where it is absolutely necessary to recover the geometry. To evaluate our method, we applied to a highly challenging dataset, the Mont-Saint-Michel Bay salt marshes in France. This is a dynamic coastal environment, so you can pay your attention at this timeline at the bottom right. Over a span of several years, this dataset has 38 epochs of later scanning data. Notice that their acquisition intervals are extremely irregular, ranging from a few days intensive monitoring to a gaps of several months. So this data perfectly captures the temporal irregularity challenge we discussed at the very beginning. The spatial data here is also irregular. So look at the three different acquisitions from our datasets. The first one offers a wide coverage but moderate density. The last two has a denser density, but it has a different footpoint. So imagine running standard M3C2 directly between the two epochs with such different footpoints and densities. It would produce a massive amount of gap due to the insufficient local point density. So to evaluate our method, we established a set of experiments. So first we took the high-density point cloud from the dataset to serve as our reference data. We then downsampled them into a sparser test dataset. We fed this test data in our time-adaptive method as well as the standard M3C2 and a fixed window baseline. And then we evaluate this method against the reference data. We tested our method under two strict scenarios. First is the spatial sparsity to see if we can recover data in low-density areas. Second is a much harder temporal gap scenario where we completely delete the entire target epoch from the input to test the method's ultimate robustness. And the evaluation metrics are listed here, so we can evaluate them in completeness, accuracy, and also geometry integrity. Here are the visual results of our change detections. So first is the standard M3C2. Because of the sparse data, it fails to compute distance for over 24% of the core points, leaving massive gray voids. Now look at the top row of our proposed method and the fixed window baseline. So both successfully filled a lot of gray gaps. The coverage is much better now, but at what cost? To see that, we must look at the arrow maps in the bottom row. As on the bottom, you can see the error map for fixed window aggregation. Notice that the heavy concentrations of these deep purple and green colors along the channel banks. By indiscriminately merging 2 months of temporal data spanning across 9 epochs, it severely smoothed out the real short-term topographic dynamics, causing massive over- and underestimations. And when we look at our results, the error map is significantly cleaner, because our algorithm only borrowed temporal points exactly where and when they were needed, which achieve high spatial completeness without sacrificing the high temporal dynamic of the saltmarsh data. Now let's take a look at the numbers. This table summarizes our quantitative metrics of the error. So first, regarding the completeness, the standard M3C2 only have about 75% of the valid results. Our method boosts this to over 88%, recovering missing data. And you can see also the two error metrics here. Our method significantly reduced the error metrics compared to the fixed window baseline. To conclude, we introduced the concept of an adaptive spatial-temporal neighborhood into the point cloud change detection method. It resolves the problem of irregular spatial sampling and missing data in real-world 4D monitoring. Also, by aggregating data adaptively rather than blindly, we significantly increase the completeness of our change map compared to standard M3C2. And we improve the geometric accuracy compared to the commonly used fixed window aggregation approach. However, our method assumes that the local topography remains relatively stable within these expanded temporal windows. So if an extremely rapid and high magnitude event occurs, it might average it out. And now we are currently developing temporal weighting strategies to better avoid introducing noises, and we'll validate this further using virtual laser scanning data. And we are actively integrating this spatial temporal search directly into the open source Pi4D library. Thank you for your attention. You can check our project below this QR code listed.